Hi, grade 12s. Today we're going to go through lesson 5. I'm in unit 5.2. It's an introduction basically to acids and bases. We're going to go through a couple different definitions of that and then talk about acid-base pairs for this one. Now you have the notes for this, or do you? Hold on. No, you don't. Never mind. Yeah, you're going to have to take the notes for this. Yeah, write them down as needed then. Okay, so the first definition we're going to look at is called the Arrhenius definition. So the Arrhenius definition of acids and bases, this is kind of the one that we're used to talking about. So an acid we would define as any compound which produces hydrogen ions when it dissociates. So you put it into water, what you get when it breaks apart, you get H plus and something else, okay? So the example here, we've got this acid here, which you now know is called sulfuric acid. So H2SO4 is going to break apart and dissociate into two H plus ions and the SO4 2 minus ion. So because this happens, that makes this an acid. Now, bases are defined as, by the Arrhenius definition, are defined as any compound which produces hydroxide ions. So this would be when it produces OH minus when it dissociates. So we've got our potassium hydroxide here. So KOH is going to break apart into K positive and OH minus. So this OH minus here is what makes it a base. Okay, so these are the Arrhenius definitions of acids and bases, and this is kind of what we've, up until this point, known our acids and bases to be. Now, not all compounds fit these definitions, so we need another definition, basically. So, for example, when we have NH3, so when NH3, when you put in, which is ammonia, when you put it into water, you end up with a basic solution. Now, in order for something to be a basic solution, we need an OH minus. There is no OH minus to be seen here, so that tells us that something else is going on here. So it's not only that it would release or dissociate into an OH minus, so there's something else here. So we have something called the Bronsted-Lowry definition. Now this is actually this little line through the O here, but I couldn't find the symbol on the keyboard. Anyways, we'll just use it as an O. So Bronsted-Lowry definition. Now when we go through these, note that whenever we talk about H positive, that is referred to as a proton. Okay, so if we talk about a proton, what I'm actually talking about is our H plus here. Now, an acid then is defined as a proton donor. So what this means is that it gives an H plus, whereas a base is defined as a proton acceptor. So it accepts an H plus. So we're not actually talking about OH minus at all anymore here. So for example, we've got our hydrochloric acid, which is our HCl. When we put that in water, we end up with H3O plus and Cl minus. Now, here's another thing. H3O plus is the same thing as H plus. Okay, so those are the same thing. Chemically, they're going to behave exactly the same. This is called the hydronium ion. The hydronium ion. So we are going to use the hydronium ion, and it is interchangeable between H plus and H3O plus, okay? So when we look here, we've got hydrochloric acid plus water is going to H3O plus, or the hydronium ion, plus the chlorine ion, Cl minus then. So if we look at what's happening, if we look at the reactants first on the left side, so which one of those is the acid and which one of those is the base? Now, to figure that out, you want to look at where the hydrogen, where the H plus is going, and you know that by looking over here. So by looking at the products, you know the Cl minus here is by itself, right? So that tells me that this H plus got donated to the water. Okay, and so when it got donated, now the Cl minus is by itself, and the water here has picked up another H plus to make it H3O plus. So this one is my donor, proton donor. proton donor, and this is my proton acceptor. So I can define this one as the acid, and the water here becomes the base in this particular example. Good. So the H2O accepted the H+, that makes it the base, and the HCl donated the H+, that makes it the acid. Okay, so let's go through another example here. We're going to use this ammonia here, this NH3. So looking at this, I want to look at the products to figure out what's going on here. So an H+ is being donated, so I have to figure out where it's being donated from. Now, if I look here, I've got NH3 and NH3, and then I've got NH4+. So that tells me right now that gained an H+. Whereas if I look at the water, H2O went to OH-, so it lost an H+. So what ended up happening here was the H+ left the water and went to the ammonia. So in this case, the ammonia is the proton acceptor, which makes this one the base. The water is the proton donor, which makes it the acid. And now, and this is where we get our OH- from. So this is why NH3 is considered a base, because when you put it in water, it takes one of the H+, one of the protons from water, leaving OH-, and this is where we get our basic solution from that OH-. Now, what do you notice about water in the two examples? So if we look here, water in this particular example is an acid. If we look at the above example here, water is a base in this example. So water is an acid and a base. So how can that be? Well, the reason is a substance can be classified as a Bronsted-Lowry acid or base only for a specific reaction. So we don't use this definition outside of a particular reaction that's happening. And so water, like you just saw in the two examples here, it can be both an acid and a base, depending on the reaction. And so in that case, we call it amphoteric. So that word amphoteric would mean that something can act as an acid as well as a base. All right. Now, we've got reversible acid-base reactions. So reversibility within our reactions, and of course we saw this in our equilibrium unit here. So we have equilibrium going back and forth here. So both the forward and reverse reactions involve acids and bases. So you have to look at them both separately. So if we look at the forward reaction first here, actually the question here is which ones are the acids, which ones are the bases. So basically you're going to look at where the H+s are going, okay? So you have to track them through here. So if we look first at acetic acid plus water, and that is going to become the acetate ion and the hydronium ion. So that tells me in the forward reaction, this H+ is being donated to the water. So that makes this the acid and this the base, because the water is accepting that proton, so it's acting as a base. So that would be the forward reaction. Now, because I've got the double arrows here, I need to look at the reverse reaction as well. So if I think of the reverse reaction happening, which is the acetate ion plus the hydronium ion becoming acetic acid and water, I can see that the H+ from here is being donated to the acetate ion. So this would make H3O plus the acid, and the acetate ion here, the C2H3O2 minus, the base. So for each part of the reaction, I have acids and bases. Now, so we're just going to label those as such now, and then we're going to bring in now the concept of acid-base pairs. So conjugate acid-base pairs. So within every reversible acid-base reaction, there exists these pairs here. These pairs are only going to differ by one proton. So here we've got the same reaction as we just did on the last slide here. So I'm just going to copy here what we did. There we go. So this is my acid, my base. Okay. So same reaction here. So we can identify the acid-base pairs, and they only differ by one H plus. So my first conjugate acid-base pair, so I've got an acid-base. So those are conjugate acid-base pairs. And if you look there, you've got H3O2 and C2H3O2 minus. So they only differ by one H plus. So it's important to note that they don't just differ by an H, they differ by an H plus. So not just the hydrogen atom, it's the hydrogen ion. Okay, so be sure of that distinction because they are different things. So these are conjugate pairs. And then we've got these ones here. So the water and the H3O plus are also conjugate acid-base pairs. And again, they differ by one proton or by one H plus. So I'm just going to label this conjugate pairs. Okay, so those are my two conjugate pairs that exist within this reaction, and each acid-base reaction like this that has reversibility will have two conjugate acid-base pairs, and that's what your assignment is going to be on here. Now, we can also just without having to draw out the whole reaction, we can just look at them and say, okay, well, if I give you an acid, I would like you to give me the conjugate base of that. And so because we know that they only ever differ by an H plus, to find the conjugate base, we can just subtract an H plus. So we'll do the first one together, and then I'd like you to try the next two on your own. So if you are oh geez, this is missing a, sorry, that's missing a positive. So looking at this, we're going to subtract an H plus from each. So H2SO4, I'm going to take away one hydrogen first. So I'd say take away one hydrogen. So HSO4. So instead of two hydrogens, we've got one. And now I'm going to take away a positive charge, leaving it with a negative charge here. So HSO4 minus. You can try the next two on your own. Pause the video. And so now NH4 positive, if we were to take away an H plus, we're going to end up with NH3 positive, but then you take away the positive, so it's just NH3. HCl, take away an H plus, we end up with Cl minus. So the conjugate acid-base pairs, again, always differ by that one H plus. Now, this one is to asking you to give the conjugate acid of something. So if we want to give the conjugate acid, the acid is the one that donates the proton, so it's always going to have an extra H plus as opposed to the base here. So if we have water, if we want to find the conjugate acid of water, we're going to add an H plus. So for this one, it's going to be H3O plus. And then for SO4 2 minus, I'm going to add an H plus to that. So it's going to be HSO4 minus. So instead of 2 minus, we added a positive to make it 1 minus. Okay. Now your assignment for this, you've got a worksheet on Bronsted-Lowry acid-base pairs, and then so the first page is writing the equations, and so you're just doing basic, well, it's got an example in the assignment, but you're basically just doing this. And then if you flip the back page of that, it's more this stuff here. And then you're also asked to write the equation as well. The answer key is posted, so you can check your work there. And that's about it, I think. Thanks, everyone. Bye-bye.